Welcome to the ML lecture. Today we will continue with our part about evaluating effectiveness, which is a core component in designing ML applications, in testing ML systems, and in really bringing ML to the world. So we'll have a further look at this. And last time we discovered that there are some ways to count how effective a network or an ML model is. And today we'll get a more theoretic view of this, and we will see how our models perform later on. But there are some tricks to learn here that you'll also be able to bring into practice and really work with, and that are really the foundation of everything that ML people do all day. And there are certain things to do wrong. So in the end, you will learn about how to avoid errors that lead to significant over expectations to your models that are just not true. So you've heard of overfitting before in the lab, but today we'll have a more close look and a more in-depth view into how we can evaluate systems in order to prevent or at least detect overfitting and similar effects. So quick recap of this example. We basically have a space of objects, and we have our gamma function, which gives us our classes in this case, just two classes, spam classification, for example, for emails. And we basically have human labels, but now we want to build an ML application out of this. And the idea is that we take our object space, and using our function alpha, we put our objects into a feature space. So out of each object, we get a small vector, in this case here, just two components. And these are supposed to resemble what our objects really are about. So in this course, we'll not go into very much detail on how to design these feature spaces, but I think we already teased a bit that this might be based on manual feature engineering. So for example, for spam, the word Bitcoin might be a strong indicator that there is spam happening, so you might want to count that word, for example. On the other hand, feature engineering today is mostly automated and driven by large language models, for example, that are pretty strong in just deriving vectors out of objects. So what you can see here is that this is a form of multiset. So it might be that multiple objects from this object space here map onto the same vector, and we will see how that ends up later. You can think about what your expectations would be, whether this is good or not. I mean, there are two cases that you could consider. The case that both classes are the same for these objects that collide here, or the case where they aren't. And we'll especially have a look at the latter. So what happens now is that we want to take the feature space and apply a kind of classification model, in this case just a linear separation, and in the end we get our classification predictions, ham or spam. And now the idea was that Martin introduced last week, that we can simply count how often this works out and how often this doesn't. And this is pretty straightforward. The only thing we have to really take into account here is the total number of objects, or in this case features, that we want to consider, because our error is supposed to be a rate, so out of 100% or out of 1. So we take the entire population as our base set, which is a bit tricky here because we have a multi-set, but what we really do is we just take the number of our objects here. And this feels very intuitive, right? Also, we consider this a true error because for every object that we estimate, we have our ground truth coming from a real human labeler that really knows what they are doing, so on. So now the question is, what limitations come up when we consider this? And the first limitation that we see immediately is that we often don't have labels for our whole data set, or that we don't even know how our whole data set looks like. So consider an online scenario. So online in this case doesn't mean anything internet related, but rather that data keeps coming in over time. Unseen data keeps coming in, which can be produced by a machine that's running in a factory and that's continuously measuring the incoming objects, or it could be some users of your system that continuously generate error logs or user requests and so on, or online comments. And you immediately see that this is pretty limited, especially in cases where you no longer have finite data sets. So think about generative models and so on. Nevertheless, this intuition that we built here is quite strong, and now we'll see how to transfer this into an environment that is actually grounded in probabilities. So the idea here was, let's just take a probability function and assign a probability to each combination of features and classes. And for some classes, or for some features, this works out. And when this works out, we don't have to penalize it. We just add the value 0 there. But if it doesn't work out, and if we assign the wrong class, and this is where this y here comes in, if we assign the wrong class, then we count 1 for this, but multiplied by the probability here, and the probability, if you have a finite set, can just be assumed to be 1 divided by the total number here. So you see the resemblance. You can simply rewrite the upper definition here with the lower alternative definition down there. But the advantage is that you now have a formulation that actually involves probabilities, and probabilities work really well with infinite data sets or feature spaces and so on. Okay, here we have the computing example. So the question is, how can we improve this? Well, at first we need to detect that we have a flaw in our effectiveness. And then, once we detected this, we have certain approach vectors. One thing that we cannot improve is the labels. There are approaches that go into the direction of active learning that just involve the idea of detecting cases where the model thinks that a human label might be wrong, and then having another human re-annotate it. But of course, the general objective is getting very high label quality. So yeah, of course you can increase the number of examples, then you're expecting your model function to generalize better, and you're expecting it to work better in the end. And you would also expect the error then to decrease. That's the whole idea. So what we can now do is we can get a more formal definition of what we just wrote, but still on a finite set of objects, which you can see here, which we map into the feature space. And again, you can very clearly see the collisions here, that objects 2, 4, and 5 map to the same point in the feature space. In reality, you often have similar collisions, but they may not be on the very same feature, but rather quite close, especially if your feature space is just real numbered vectors with a certain dimension. Then it's not that likely that they really map to precisely the same vector, but what could be is that realistically that they are very close, so closer than a model separation boundary model could really separate them at. So we get the vectors here, we get the classes by our ideal classifier, which can be human, and we get our model function, which then assigns classes. And what we immediately can see is that we have some problems here with this class for example 6, which should be class 2, but is classified as class 1, for example. And in cases where this is not rooted in a collision, so for example for this misclassification, we can see that this stems out of a case where we would have to correctly map both C2 and C1 on the same spot. So obviously we cannot do it. This is a problem in the derivation of the feature space. But in cases where we actually don't have this kind of collision, we can use machine learning technology. We'll come to what this means to actually tackle that error. Yeah, and if we have this label noise or if we have collisions, we cannot do it. So here again, the definition that you also saw last time, which really means that we divide by the number of objects and count how many misclassifications we get. So true misclassification rate. Another question is, how can we estimate this? Because as I said, we don't always have the full data set. We don't have the full data set annotated neither. So the question is, what can we do to estimate this in a feasible manner that's also computationally acceptable? And in order to do that, we'll also have a look at a probabilistic foundation for this. And I will try to point out the correspondence to the formulation that we just saw, the frequency-based. But first we have to introduce some terms here. So what we have is a probability measure and a sample space, which means that we have some object that provides us with randomness. That's the idea, but mathematicians don't really like randomness unless they can formalize it and control it. So they introduce this sample space and probability measure, and this really allows us to control and formalize how probability works here. And what we want to have is two random variables, one random variable x, so note the difference in notation here, and one random variable c. And the basic idea is that our random variable x controls how often each feature comes up in reality, so in our data set or in our online setting where data sets examples keep coming in. And C basically controls how often which class comes up. So what you of course have to admit is that there is some correlation between the two. Like, it wouldn't make no sense if they were independent in the sense of you have a feature and you have a class and they have nothing to do with each other. Then we can just let the whole machine learning thing be, because what we are doing here is we exploit the correlation between our features and our classes, in the sense of that we ask ourselves, if we have a certain feature or feature vector, what classes should we predict? So we need to find a mathematical way to somehow denote this correlation. And what we do here is we use probabilities. So we can take these four notations here for probabilities. So this is the event-based notation on top, and this is just how we can quickly write the same thing down. But this is a bit overloaded in the sense of that you need to have a look at what kind of objects you're putting in here. So what's the idea? This is the probability of us getting a certain feature. This is the probability of us getting a certain class. This is the probability of getting a combination of a feature and a class. And this is the probability of, under the assumption that we get one class, that we get a specific feature. So conditional probabilities are introduced here, and in the lab we later also learn how to compute or calculate with them. And this will really help us exploit this idea. And now we can basically just replace the probability or the feature-based or frequency-based definition of the true error rate with a way that incorporates this probability here. So this basically looks like the formula that you just saw, but what we have here is a probability now, and it's summed up over all features and all classes for these features. So all combinations of features and classes, we check how likely that combination is and whether we would be able to handle that combination well or not. If we do handle it well, we don't get a penalty. If we misclassify in this specific case, we get the penalty, but it's weighted by the probability. So think about what the background is behind this formulation. So for example, if you have a model that is defined on a data set where some case is really rare, then this very rare case should not be taken into account with the same weight as a very common case that basically comes up in 90% of the cases. Sometimes you don't want that. For example, if you're working in security-based applications, so at the airport, for example, airport security, and you're designing a metal detector, then you're better off checking some more people manually than you are letting someone through bringing something illegal. And the latter case is probably really rare, right? Like 1%, for example. So what ML would do here is just say, okay, I have a probability, and this probability is that with the sensor going on, this is the feature, the probability of the class is still really low. Like still almost no one carries something illegal if the sensor goes on. So you don't really get a strict penalty for that. So the idea of the model could just be to, okay, let everyone pass through, and you don't want that. So take this with a grain of salt, but also consider what this probability here means. And in the lab, we'll later discover some ways to actually re-weight this so that we can better incorporate such cost scenarios. There's also a slide at the end of the deck here. So what's also another problem? We don't know this probability, because this would require insider knowledge about how the whole process underlying my ML model works. Because we don't know all possible combinations, we don't know all possible ways to assume these classes, but what we can do is we can, for a certain given class, estimate the probabilities that some features come up, and we can do that under a certain assumption, the naive Bayes assumption, and we'll get back to that in a minute. So this will be one part of this idea of let's estimate the true misclassification rate using some tricks that help us to actually derive these probabilities, because otherwise we still cannot compute this really. So this is another way to express this, and I think this is where you stopped last time. What you see here is the map of features or feature numbers and class numbers into the space of joint probabilities. So dark square in this example means high probability that this happens. But the question now is how to interpret these values and how this will help us in actually seeing how to deal with these errors. So the idea here is that if you have a certain x, so a certain observed feature, and this is what you get as the input of your ML process, it's easy to see which class you have to assign because it's unique. So let's pick one column here, for example, this one. You can see that there's only one class that has a non-zero probability. And this is basically the dream of every ML engineer, simply because you can't do anything wrong. You just learn the direct mapping from X to your class and just say, okay, in case that we have this X, just take this class as a hash map, for example. But reality doesn't work like this, unfortunately. So what we introduce here, okay, I took this example column here. What we see is that we have some label noise, and actually it's not that unique what class we could choose. So in some cases, when we observe this certain feature combination here, or feature vector, it will occur that we have this class. In some cases, we have this class here, but there's still some form of probability here that we can observe. So now let's think about what the probably best thing to do here would be. What should you choose in order to make a best educated guess? Yes? The darkest square. But you just don't consider everything else here. You just consider this column here. And in this column, you choose the darkest square. Okay, different example here. But nevertheless, we'll give this method a name later on, and this will be the naive Bayes classifier. Okay, and here we have it for all labels, typical label noise scenario. All right. And this is the Bayes classifier. What you basically do is you identify the feature vector that you have, check on this vector of probabilities here, and choose the maximum one. So we take the argmax here, okay, multiple examples, so on. What does argmax mean? Basically it means give me the number of the class and not just the probability value that's maximum. Then I don't care about that. So let's also have a look, I already teasered this a bit, at why this is the same. So actually in the definition of the conditional probability, you can see that these are dependent on each other, and just their difference is a constant factor. And I quickly write this on the chalkboard. So the conditional probability is defined as the joint and unconditional probability defined by the probability of our X. But if we are just choosing our C, so C is the only thing that we can vary here, then this thing is constant. So it doesn't really matter whether we find the highest value for this or the highest value for that. So this is why they are the same. But now let's also have a look at what this means mathematically or intuitively in this joint feature space here, or joint probability space on the feature space. So this means that you're actually scaling up this vector by the sum of the whole column, which means that the sum of these values after scaling with this is 1 again. So you have probabilities. These conditional distributions fulfill everything that we expect out of probabilities, and this will be really useful later on. And it also makes sense here, right? You can scale it up or down, scale it to be some 1. The maximum value still stays the maximum value. And now we can actually compute the error that we would get out of this very naive method. And this is, yet again, just the same definition, but we can compute this error value here. So it's basically the sum of all fields that weren't selected. So here, for example, you select this value. So you sum up all the others because they go wrong. And this forms your error function here. Yeah, so this is the sum of the whole column. And what you take away is basically the one value that you selected because that's correct. And this is again your error. And this perfectly fits in our previous definition of how to do this. And what you can actually do is prove that this classifier is the best possible classifier that you could really get on your given definition of features, and on the assumption that given one feature vector, you can only choose one class, basically. So here we have another view of the same thing. But what we want to have a look at now, a bit closer, is the marginal probabilities. So basically the sum of everything that's behind one of these bars. And you can see, I mean, this looks like something that you could imagine as a probability function. Same thing here. This is basically just the probabilities that any of these, or that one specific one of these classes will occur when you are just given some objects. So actually this will be very handy in the lab when we'll have a look at actually computing naive Bayes and seeing which of these underlying probabilities are more common or not. So what we just saw is precisely this marginal distribution here, basically the sum of the whole column. And scaling the whole thing up again means taking the conditional probability. So given the knowledge that we have for our objects, our certain vector here, what is the class? And those class predictions then, or these probabilities, should sum up to 1, right? That's intuitive. And you can also do it the other way around. So these are the marginal distributions. So now we have it in a real scenario where we're learning a separation boundary. And again, we have some probabilities that we can assign here. So the idea is that our classes, wait, let's check the axis here. So for our features on this axis, we get some where we are pretty certain that they are class 2. So for example, here in this region, we are very certain that this is class 2. And here in this region, we are very certain that this is class 1. And the question now is, where should we place this boundary? I mean, yes, in this case, it's pretty easy. We just put it here in the middle and no discussion around there. But of course, you can imagine that there are some cases where this is more fuzzy and you have some pluses leaking into the area of the minuses. So again, you really want to optimize the error here. And again, we can take these functions as the joint probability functions. And you can see that class 1 is a lot, or a bit less common than class 2. And you can also see this in the area under this curve. It's smaller than the area under this curve. And if we want to correct for this, we can scale it up. And this is exactly what this conditional probability means. So now the area under both curves is 1. So back to the question that I introduced in the beginning, the question of what the true error really is in a real scenario, because we cannot compute it, unfortunately. We will never really know what the true error on our probability distribution is, simply because we cannot know what the probability distribution is. There might always be some aspect that we didn't consider yet. So for example, in an online scenario where some samples are still coming in just after the model has been trained, there still can be some effect that we didn't consider and that really gives us some problems in defining our error. But nevertheless, we need some way of estimating it, and we'll have a look at a few ways to actually find bounds for this error. And this is also what people are doing every day when they are training ML models. They are asking themselves, how can I estimate how good my model is, and how much can I trust this estimation? So important part here. And we basically have a typical relation here between all these things that we will get to know now. So this is our target, so to speak, our true error, but we really have no way to compute it. But what we can do is we can compute some of these values here. I'll explain in a bit what they are. And they should be quite close, if we do everything right, to the true error. That's our hope. And there's also one thing you shouldn't do, which is taking the training error into consideration. And we'll have a look at why this holds in a bit. And the basic idea is, if you have a dataset selection that's quite small, you're underestimating the error because you think that the problem is easier than it actually is. But if you increase the size of the dataset that you're working on and that you're training your model on, and especially that you're testing your model on, up to like considering every feature there is, which might be impossible again, but then you will reach the true error. So this is the motivation why people in ML are all the time searching for the biggest data sets. So if you're downloading some data sets online, there will be metrics reporting on how large they are, and people will favor some data sets, for example, on text classification over others just because they are so large. And this is also the reason why in our research we're maintaining a cluster with petabytes of web data, just because scaling up to a absurdly large dimension still brings us closer, or brings our models closer in estimation to the true error. So if we test our model on the whole internet, basically, then we have a pretty good test on how it will perform in the future, but also in training. Similar effects exist for training. So if you train on more data, of course, you would expect to get better results if your model can keep up with it. So what you should never ever do is report your training error. Because if we just learn our values by heart, and you saw that by just taking our x values and just taking some class and assuming that it's the only class that exists, we get some error, yes, but we can cheat and simply bring this error down to 0 in case we have no collision by simply overfitting and not generalizing on our model. So the same is, I don't know, with learning vocabulary or learning from a textbook. So what you can, of course, do is taking the textbook and learn it by heart, learn every word that's in there. But nevertheless, you might be unable to do the same calculations on different tasks because you just memorized how this looks. But nevertheless, if someone else asks you or tests you, like, please test me for my exam, and just asks you a page out of this book, of course you will know. And of course the error will be 0. So you can cheat by reporting the training error. And people in ML are pretty good in spotting that, actually. But we have some examples where people failed to spot this in a smaller extent in the lab later. So this learning by heart and not generalizing and not being able to actually work on new examples is called overfitting. We'll also look at this later. And this difference between one error estimation that I will come to in a bit and the training error, this is called overfitting or caused by overfitting. And so using these methods, cross-validation error and holdout error, to estimate the true error is supposed to eliminate the effect of overfitting on our error estimation. So here we have a smaller explanation on what these components are. You can have a look at this later, but basically the idea is that you put in your classifier and a data set, which can be quite small, but you shouldn't make it too small. And for the holdout error, you test it on different data than you trained on. That's the idea. And for cross-validation error, what you do is you test on a large data set, or you operate on a large data set, but what you do is you train on one part, test on the other part, and you do it a few times in order to not overfit on the selection of the test data set. We'll come to that in a minute. So again, this is our frequency-based error definition. And what we basically get for the training error is, yeah, we just train our model on a data set and test it on the same data set. And of course, this doesn't detect issues that lie in overfitting and so on, because we have a quite bad estimation of how our real data behaves in this case. The idea of holdout error is that we do a split into a train test and a test set. So this is our training set, and this is our test set. And we train on this part, and we test on that. So the idea is, if you get back to this textbook example, like take some of these exercises out of the textbook, write them to a different sheet of paper, and erase them from your textbook permanently. If you now learn the textbook by heart, at least you will fail in the real test. I mean, this is also the reason why they are like in school, there are 2 editions of textbooks. One is for the students, one is for the teachers. And basically, they have the same distribution of exercises, but it's supposed to function as a holdout set, so the teacher can actually test the students on unseen exercises. This will not help them learn. So in order to learn, of course, you should still train or practice on the whole set. So something that we'll also cover here in a minute is actually doing this test, checking how well your model generalizes, or how well your students perform on unseen tasks in this analogy, and then scrapping the whole thing and retraining the whole model on the full data set. Then you cannot estimate the error anymore, but the assumption would be that the whole model is performing better than this toy model here. So you have a lower bound of the error that's actually given there. So you're saying like, on upper bound of the error that's supposed to happen there. So you're saying basically my model will perform better than that. From ML practice, I can tell you that this is often not done, in the sense of that datasets these days are often so large that people just define a very small test data set, which still might include thousands of examples, but compared to the whole data set, it's so small that it wouldn't really make an effect when you take it into account in the whole training. So you better save on the resources, better just develop a good model that even on this training set performs so well that you can basically sell it and give it out to everyone. And all the models that you can download online, on Hugging Face and so on, are basically just trained on the training set, tested on the test set, and not retrained on the whole thing. But the idea still holds, and we also have it here on our slides. And again, how can we compute the holdout error? It's frequency-based, pretty easy. Again, we just take the test set, check the cases in which we classify them wrongly, but on the model that was trained on another set. And again, we divide by the number of examples in our test set. So the error definitions here are pretty easy if you know the basic frequency-based error definition. But the problem here really lies on finding good representations of train and test set. And here we get the next problem. We really have to take care when splitting data into train and test data, because data is not independent and there might be an unseen correlation or unwanted correlation between the training and test data that we then don't see in our real data. And I have some pretty nice examples in the lab also, where we have a look at very famous cases where this went horribly wrong, so to speak. And people did a correlation or did a test set split with a correlation between training and test data. This led to the whole system overfitting on this correlation, but you couldn't detect it because in the test set, the same effects would happen that you already learned on and overfitted on. So in reality, this model performed really poorly, but no one was able to detect it, because this is our only means to ever detect or measure how good our model is. So this is, again, as a pseudocode, the same thing. First, we train on our data set until we're done. And then we train on our training data set again and test, but only on the training part, and test that toy model here, test that on the test set. And what you would actually report in this formal holdout error algorithm definition is this Y, so the model trained on the whole data set, plus your performance that you observed on the model trained separately on just the training split of the data set. So you're basically doing the same work twice, but on different data sets. So just that you can have something trained on the whole data set and incorporating all that knowledge, and that you can have one model where you're actually able to report the performance. Yeah. So now the question is, what happens when we actually overfit on the selection of our training and test split? So it might be that you actually run into a case, especially on very small data sets, where accidentally your model performs really well on the test set, but not on anything else. And you really want to avoid that. Like, and this case is easily imaginable. So for example, if you consider this textbook example where you're solving exercises again, it might be that the exercises you put into the test set are actually the easiest ones. And there's always some exercise that's easier than the others, right? So in case that you put them into the test, again, you test that you didn't memorize all the examples, yes, but you're blatantly underestimating the difficulty, basically, of the whole thing. And the same can happen pretty quickly with ML models. The idea is to make the test set large enough so that it includes not only the easiest, but also probably some other examples. But sometimes your base data set just isn't large enough. So if you're talking about medical applications, for example, you have a limited number of patients that you're doing your research on. You can't just say, okay, scale it up by factor 100. It's not feasible. So what we can then do is we can actually pretend to play through all combinations, with some exception, that are possible in choosing the test set. So what we could do, but this would this would cause much effort, but it's also described, I think, in one of these remark slides, is we could take all possible selections of test set members out of our data set. So choosing binomial coefficient, choosing a certain number of data out of our whole data set, then training on all of these combinations, testing on all of these combinations, but the effort increases exponentially on the number of test set members. So we don't really want to do this, and what we do here is a simplified approach, k-fold cross-validation, and k means, in this case, that we're just taking k takes on the selection of the test set. And we do this by splitting up our data set into k parts. And in the first case, we train on everything but the first portion. In the second case, we train on everything but the second portion. And then we always take this green part here as our test set. So we're not playing through every combination that there exists of the selection of test set members, but we have a good shot at it, and we can especially beforehand specify the effort by just saying, okay, I can afford training the whole thing this number of times. So how many models are you actually training here? Yes? Okay, you're training k models here, but what are you reporting in the end? So you're reporting a performance limit. You're saying like, okay, my model will probably be better than either the worst of these or the mean of these. We'll come to that in a minute. But what model are you actually reporting or giving back, returning? Well, yeah. Exactly. You need another model that trains on all the data because these models are performing poorly, probably, on their own. But again, you would assume that if you change something on the whole model, you can report on that. Well, often case, again, today, people assume this effect to be negligible simply because if you have a high enough k, there's almost no difference between training on like 99 samples and training on 100 samples or portions. But nevertheless, our algorithm here demands that we actually train on the whole thing again. And the cross-validation error here is defined as the mean of all these individual holdout misclassification weights. So pretty intuitive in this case. And the idea is that you can average out or smooth out effects that come by choosing the test set. Okay. So often case you are not just training on one model, but you're training on model variants. This is very common, especially in neural networks, since neural networks not only have parameters or weights that you can tune via gradient descent, for example, so the computer does all the fine-tuning of these models, but you also have cases where model hyperparameters are introduced. For example, the number of layers in your model. To answer what number of layers will perform best on your specific data set is not trivial. So the best idea would be to try it out, right? So now the question is, on what should we test and how should we test trying out all these variations of hyperparameters? And the idea basically is that we have another split. So we not only have our training set and our test set. The test set, again, is used to report the performance of the model. But we also have a validation set, in purple here, which is just used to determine which of these hyperparameter combinations is the best. So think about why we need to do this. I mean, what we could do is simply take the test set performance for each hyperparameter, because this is conditioned on the hyperparameter setting. So for each hyperparameter setting, we compute the test set performance, and then just take the one with the best test set performance, and that's it. What problem could we face here? Again, the whole scenario here has been done to avoid being fooled by overfitting. So you really want to rule out any effect that could lure you into thinking that your model performs better on real data than it really does. And the same can and will happen in this case also. Oops. In this case also. For example, there might be some hyperparameter set that just works so well on this specific set of training data, but totally fails in reality. This becomes especially a problem when your hyperparameter set or your hyperparameter space is really large, because then you can basically encode the whole model in the hyperparameters. This would be like guessing a password, but you can try out every combination on a new computer, and it never locks you out. Of course, at some point, you reach the point where you're overfitting on the selection of hyperparameters. And in order to avoid this, we need an unseen holdout set again that never played a role in determining the hyperparameters. And the best practice really is train your model, test it on different hyperparameter sets on this validation set. Then you come to the conclusion, okay, this is the best model, and only if you write this up as a paper or as a business report, I don't know, you run this test over here once and report the performance. And if you're not satisfied with this, strictly speaking, you're not allowed to go back and change something in the model, because if you do this often enough, again, you're overfitting on your test set. So people have been getting really strict with that. So if you're writing a paper, submitting it to NeurIPS, for example, ML conference, people will kick you out or kick your paper out for doing this wrong and actually overfitting on your parameter set. So this is called p-hacking also, like hacking in the sense of taking your hyperparameters and playing around with them until you reach desirable results on your test set, which is cheating. So keep this in mind. This also plays a major role in ML dataset that you see today. Oftentimes the dataset already comes with a predefined selection split of train, validation, and test. Because what can happen again when maybe 1,000 people are training a model or designing models for the same dataset? Well, someone will have the best according to this test set. But again, this could be overfitting on this whole test set scenario, because you're considering 1,000 model variants. And this has been happening with the classic computer vision data sets, for example, because in the beginning of neural network, everyone was doing computer vision because images are a good domain to work or to do neural networks on. And basically, there were like 1, 2, or 3 data sets of computer vision images, or just images and labels. And everyone was building their model on that. And people were reporting, in the end, they were reporting so marginal improvements that you could assume that this is just randomness introduced by overfitting on these. Because again, if every researcher tries to improve on that at some point and reports the error on the test set, at some point you cannot trust these results anymore due to overfitting. But again, it's really not easy to get to get your hands on this and to gain sufficient experience in estimating which cases produce overfitting and which don't. And you really need a careful eye, and you need to train your own careful eye in order to detect scenarios where overfitting may occur. But we'll also do this in the lab and have a look at some scenarios, and you'll be the investigators or the detectives trying to spot cases where overfitting is prone to be happening. Because again, we have no means of detecting this. If overfitting on the test set occurs, we're done. The only means then would be, okay, let's generate new data and do a new test set, but sometimes the data's resources are limited, so we cannot do that. Okay, and this is the formal definition. We just take the best performing, so the one with the smallest validation set error, best performing hyperparameter set. And again, the error is defined on the test set. And we can do the same for multiple validation sets in case that we suspect that the choosing of our validation set also leads to overfitting. And we take the best one in that case. So a small remark here also, I already teased this on you, is that some forms of errors associated with different classes have different costs in reality. So for example, airport security check, just manually rechecking someone is simply and easily and quickly done, but letting someone with a dangerous item into the airport is a big problem, so you probably have a high cost on this. If this was a finance lecture, we all would know, or would pretty easily come up with scenarios where the costs are just both in a binary setting, both, so for each classes, just money values. So it's pretty easy then to just define the expected value that you would get for each. And the idea is that you really want to optimize the cost value. And this has two sides in here. So this needs to be taken into account when training the model. You really want to know about your cost there for each case that you did wrong. And you really want to consider this in the testing case. And this slide here is only about the testing case, where we want to compute a cost-based error that basically sums up the costs for all the cases that we have in our test set and averages them. So this is the average cost, can be in euros, for example, for our problem that we caused. And of course, if we have the correct class, and this is why we have two values here included in the cost function, if we already have the correct class, then we are not penalizing this, so there's no cost there. So in this part of the lecture, we considered different aspects of attributing effectiveness measures to our models that we trained. And what we saw is that we really have to be careful to not be lured into false assumptions about good model performance. So again, my invitation to have a careful lookout on cases where this can go wrong.